we also have to include bonds. We saw if we did harmonic bonds, it wasn't that great, okay, because it allowed for bond crossing. So then we introduced Beanie, and this is where we ended up. Okay. Now, Beanie and this, so when we program this up, Beanie's not too bad because we only have to look at our neighbors, right? But for the WCA, which is the excluded volume interaction, we have to look for every pair of monomers in our system, right? So for every ith monomer, we have to look over all J monomers, right? This is very, very expensive. And as we saw last time, as we start increasing N, things scale horribly. In fact, how do they scale? N squared, which is nasty. Because it means if you double the length of your polymer, things actually take orders. Okay? So, is there any way we can try and reduce this effect a little bit? This N squared scaling. Is there anything we can do about it? Domain decomposition. What's domain decomposition? So first of all, let's not talk about specific algorithms, okay? Let's talk about very general ideas. What do you guys think we can do to increase the efficiency of this? Does everybody know the answer? Am I just preaching to the choir? No? Okay. So you got a polymer here, right? Oh, okay. I left these here last time. Well, the only one I use is the white. Okay, we got a polymer. And it's made up of all these monomers. Okay. And so for every ith monomer, I have to look at all other monomers in the system. Okay, and this takes forever. How can we maybe make this more efficient? Any ideas?
Can you do like a neighbor check or something?
What do you mean a neighbor check?
So maybe I'm on the wrong track here, but maybe like go to the left, right, see if there's I mean there will be things that are changed, and then look at.
The problem is that you can be close to somebody very far away, right? So we can't just look at our neighbors. Neighbors in space.
Yeah.
So neighbors in space. Yeah, a region around. How are we going to know neighbors in space? Their work starts. Right. Over then I'm checking over everybody again. That's a problem. True, right? That's what we want to get away from. So the brute force way is to literally look at everybody, see how close they are to you, and if you're closer than the distance that interactions happen, then what do you do? Okay? Check every time. Now you check every time. Yeah, and what do we do in the meantime? Just keep
using the same set.
Yeah, so what might we call it?
I'm going to say that it might be called the main key.
No, okay, not. So you have derived it neighborless. Oh, this is what's known as a neighborless. Okay? So you look around you, you go, okay, within some radius, this guy's there, this guy's, oh, this is my started monomer, right? This guy's here, this guy's here, this guy's here, right? And then their identities can be, you know, these guys will be very close to the monomer we're looking at. These guys can actually be quite far away in terms of where they are in the polymer. So if this index is 10, this could be all the way to 10. Okay? And then there could be one over here from like 500 Kelvin. Cool? Yeah? So what you do is you make a list of those. And so each monomer has a list of neighbors in the vicinity. And now instead of checking all the monomers, only check the interactions with those in the list. Okay? Of course, this can only last so long, right? So every n steps, build list.
So would you just do a calculation real quick to see where the average position of all particles is in the polymer, and then choose that region to be where you're checking? How would you select a region?
You don't. Okay. So every n steps, you look at everybody in the system.
Oh.
And you build your list. Okay. So that goes as n squared. Okay. But then you get n steps where you only look over the neighbor list. Okay, where n neighbor is much, much less than total n. Okay, this does not scale as n squared. Okay, and in fact, once you're of a certain size, the number of monomers in the neighborhood remains constant. Right? You have more particles to check over, but your neighbor itself, your neighborhood doesn't. Cool. So putting these together, it doesn't scale as n squared. It's more like log. Okay. Okay. I think so. Yeah. You can check that one.
So do you make a list for every particle?
Yes.
So you have n lists.
Yeah. Yeah.
So basically, in one step, you for every monomer, making it and checking it in the top.
Yes. Exactly. So you have one step where every monomer, you look at all other monomers, you make a list of monomers around that monomer, right? Other particles around that monomer. And then for the next n steps, you only check those. Okay? And then you rebuild it. Cool? Mm-hmm. So how do we want to figure out when we're going to rebuild? Right? Because we want to make sure we rebuild often enough, because otherwise we're going to miss monomers interactions that results are going to go right. Okay. We don't want to rebuild too often, because then we're inefficient.
You look at the average distance that or the average time it would take for a particle to leave a neighborhood.
Yep.
Or build a distance.
Yep. That's one way of doing it. And then you got to go less than that, because that's the average. Okay. Right? So another way you can do it is you can just keep track of the maximum distance any one monomer has traveled. And then when that basically crosses whatever your radius for your neighborhood is, you got to rebuild. Yeah. Cool? Is this cool, people?
Like dynamic rebuild.
Exactly. Yeah. But that way you make sure you never ever miss an interaction. Cool? Conceptually, it's very straightforward. Programmatically, it's not that much harder either. Okay, you just got to rebuild these lists. Blah, blah, blah. Cool? Okay. Any other ideas of what we could maybe possibly do? Very good job, by the way, for deriving tables. Proud of you guys. Anything else we could do? Different.
One neighborhood and theory. Or you only have one neighborhood.
You only have one neighborhood.
Oh.
Yeah. Unless you're like a quant. Any other ideas about how we could maybe move those?
Could we, I mean, going off of what Kyle kind of first said, is there a way that we could relate the, say, like the diffusion of particle to how far it would take to go out of that circle?
Oh, no. We've done neighbor lists. Now I want a totally different approach.
Okay, fair enough.
To having efficiency.
So
Just a
for
different one.
Yeah.
choosing the parameters, like how far neighbors are and how often we update, that's kind of just as a situation.
Yeah, I mean, you run into the same things. If you have too big a neighborhood, then you have too many neighbors, you're always checking over.
Yeah.
Right? If you have too small a neighborhood, then you're updating all the time.
Right. So
So there tends to be a peak in the efficiency.
and so that's kind of how I'm just curious.
Generally, go with the defaults.
Right.
The simulation.
Right.
Okay?
Yeah.
But yes, it is. I mean, you could probably derive it. okay with that? Okay, let's take a different approach. And this is actually kind of coming out of the same ideas, right? So we know who our neighbors are in polymer space, right? How can we figure out who our neighbors are in space?
What is the distance away?
I would take the average of the polymer, right? And then compare it to the average of the other polymer, and then use those as sort of like objects.
So you're saying, but we're looking at like one monomer. So again, we want to know who this guy's neighbors are.
Oh,
Okay,
you're
so-
only ever looking
Yeah, this is particle-based modeling and simulation, right? So we look at almost everything from the basis of the particle. How else can we figure out who our neighbors are?
It's not space.
No. What am I asking?
Yeah.
Okay. So we can make a neighborhood list for every particle, right? There's another way of looking at this. Let's just bin space and do a bunch of different things. Cool. And let's put every monomer into a bin, right? And so if you have a monomer in this bin here, okay, your monomer in this bin, your neighbors are going to be in this bin, these bins.
And your own bit, I guess.
Yes, definitely. Yeah. Well, depending on the size, generally. Cool. Okay, so this is different. You're not making a neighbor list for every particle, so you move around it. You're doing kind of the opposite of that. You're taking space, dividing it up into a bunch of chunks, and putting each monomer into one of the strings. Cool. Okay. This is called domain decomposition. Okay, and we have similar challenges here. How big do we make these? Well, we don't want them too small, because then you have to rebuild your domains when a particle has traveled out of the domain, right? Whenever any particle has left the domain it's in, you got to rebuild this. Cool. Yeah.
Can you not just check?
You don't want to start tracking individual particles, though, because what we're trying to do is have an algorithm where we can just move over everything quickly, have a painful step to rebuild everything, and then we move over everything again quickly.
So in 3 dimensions, you have quite a few neighbors.
Yep.
How wide is it?
Yep. Okay, so we don't want to rebuild too often. We also don't want it so big that we're checking all the particles in the system. Right?
I think how we is what you check we have the same.
Well, if I know a particle has left a bit, check which bit it's moved to, increment that one. Decrement the one.
Yeah, you can do that.
Okay.
Yeah, keep track of particles. Cool. Okay, so these are 2 ways to go about it. Whether you use neighbor lists or domain decomposition, which one is faster depends on the details of your scheme. Okay. There's one case that domain decomposition is really the way to go. Can anyone think of a case for that?
Really sparse.
Sparse system neighborhood list is probably.
Yeah.
So like this, we're all going to 100 conditions anyway.
let's say we have a polymer, a system that has a bunch of objects fixed in space, right? The objects that are fixed in space, some kind of geometry, a wall, just a post. They never move. You always know exactly where they are, right? So once you do the domain decomposition, for the ones that are fixed in space, you never know. Cool. And so wherever your monomer is, you just look at the obstacles in the region and you're done.
That's cool.
Okay? Yes, it can lead to extraordinary performance. Okay. This is a modification I did to simulation package, and some of our simulations in the lab ended up being like 50 times faster. It was ridiculous. Okay? Yep. So it is a good trick to keep in mind when you're building complicated geometry out of particles. Cool?
Is there a data that we needed?
Well, it actually was for a bunch of systems. I was looking at it's actually the project where I had a bunch of obstacles on either side of the membrane, and I was looking at translocation. But then we had another guy who was looking at gel electrophoresis, so we got a bunch of posts. And the thing is, they were, as long as they're static, you use this, it's super, super fast, because they aren't. But the choice in Espresso were either we build out of what were called constraints, in which case every particle checks every constraint, or you build it out of particles which are fixed in place, but then you still would loop over the particles that are fixed in space. Okay? So there was inefficiencies going both ways. And what was easiest to do was actually make a domain decomposition for the constraint object. Vastly. Of course, there were some bugs. Some that were still fixed. Cool. Okay. So speaking of efficiency, I actually don't want to spend time coding these right now. Okay? But I want to do more complicated systems. So what we're going to do is we're going to use a combination of both our own programming as well as coarse-grained simulation packages. Cool. One I'm going to use, which is familiar to have you, is Espresso. Not quantum espresso, but Espresso. Okay, which is a coarse-grained simulation package.
Just regular espresso.
Yeah, you probably heard lots of person. It is a fantastic program, and it's beautifully written, but the scripting language for your input files is TCL, which can be particular.
TCL is actually German for horrible language.
Okay. So, why is this nice? Let me show you what an expressive file looks like. Wow. We're basically going to let someone else do the nitty-gritty coding for us, and we're just going to use the ideas we talked about to do simulations. So, Espresso Poly, Fini, WCA, TCL. Okay, so this is just a bunch of stuff. N is going to be the length. What is N going to be? Yeah, the length of my polymer. This is just going to be a flag whether I want to visualize it live or not, because you can stream from Espresso to AMD while the simulation is happening. This is just going to be my random seed. Notice I'm actually setting it in two places here, because I'm setting Espresso seed here, and I'm also setting the random seed inside TCL. So in case I use random numbers. Here's pi, here's my maximum time. And I'm setting some variables for box X, Y, and Z. This is just opening a file. And then I'm setting my center points as well. This, epsilon, sigma, RC, shift, kappa, lambda, these are my WCA and ENI parameters that we talked about last class. Cool. Thermostat. Longevin, 1 and 1. Anybody want to guess what's happening here? Not my
Well, I don't know if you want
Okay. Get to that.
you're using really dynamics.
Yeah. Yeah.
On those options.
So Longevin dynamics, okay, both for like the method of integration, and that gives us a bit of set. Cool.
So what's this doing?
What's this doing?
Is thermostat?
So we're selecting the Longevin dynamics thermostat, okay, and we're setting two things to be 1 and 1. Any idea what we might want to set? Thermotion.
The
Temperature. Thermostat. Right? So that's temperature. The dial on your wall. Yeah. Cool. What else do we have to set? What do we add to the equation of motion for longevin dynamics? Nope, we do not add the diffusion coefficient. What terms do we add?
The second thing you added. Say that.
What?
Second thing you said.
Just right down. Right? Yeah. So what do we add to the equation of motion? Right? We start with F equals ma, and we add a drag term, a random term. And we talked about how these are not independent choices, they're coupled, right? What's the theory that couples us? Dissipation? Or fluctuation dissipation? Right? It says these are linked, so the fluctuation coming from the random term linked to the dissipation by the drag term. Right? What was one of the key variables in that relationship? It appears in the prefactor of both the drag term and the random term.
Yeah.
Yeah. Friction coefficient. Right? So, Longevin dynamics, you need to set the temperature and the friction coefficient. Okay? And notice that D comes out of this because D, the long time limit, is KT, which is the first term, over theta, which is the second. Cool? Remember to write that? Okay? So there's a lot of physics in this little statement. Okay? And that's the physics of the last 6 weeks. SetMD are just commands for the program. So we're setting the box size. We're selecting periodic boundary conditions in X, Y, and Z. We're setting the time step to be 0.01 as we've done in the simulation. And we're setting the skin to be 0.1. Okay. Now, some people in my lab were supposed to investigate what this skin command was.
Thought we were talking about.
Nope.
But how close you can get to the boundaries of the main decomposition before it decides that you're close.
I think even like the Berle list. This is somehow linked to the Berle list as well. When you cross this, you rebuild the list or something. Okay? It's basically a dimension for that sets. Basically the size of your neighborhood, your domains, and how often you update them. Cool? Not precisely that. Okay. You're the guy that was supposed to look it up. So.
You're within that distance.
Don't worry, I'll look at that.
Okay. Anybody want to guess what this command is doing?
Yes.
Linear interaction.
Yeah, what kind? A Leonard Jones? Yeah. And it's choosing an epsilon, a sigma, a cutoff, and a shift. And so if I choose epsilon 1, sigma 1, RC to be 2 to the 1 6 times sigma, and a shift to be 0.25, what do you think this is? WCA. Okay, notice it's 0.25 because here the shift is inside. It's multiplied by the 4. Okay, so that's why 0.25 times 4 gives you 1. So we've been writing it to finish it. Excellent. Cool. Okay, but remember the shift doesn't actually matter. We'll talk about that in this class. Okay? Unless you're doing energy calculations. Okay. Okay. How about this guy? This is a very nebulous. It's not an impulse. What do you think this is doing?
This is our 3D interaction.
Yeah, it's just defining a beam direction. Okay, 30 and 1/5 should really be my kappa and my lambda. Cool. And we'll worry about this command a little bit later. What am I going to do? So this is the glory of TCL. Put spaces everywhere. Put $signs everywhere. Okay. I'm going to loop over n, and I'm going to place objects. My polymer initially is going to be laid out along the x coordinate at the center of the box and y. Cool. So I just keep it in x. This command just creates the particle. All right. This $sign I is the index position XYZ, and I'm going to give it a type of 0. So Espresso is very type-based. Okay, I'm going to see how this is important later, because I can define different types, and then I can define different interactions between those types. So if I want particles of 2 different sizes, I define 2 different types, right? And then type 0, 0, let's say, interacts with the size of diameter, effective diameter of around 1. The other one could have effective diameter around 2. And I can use my combination rules for the interaction between 1 and 2. Cool? Okay. And what I'm going to do is say if I is greater than 0, so not the first monomer, I'm going to bond particle I via bond type 0, which is my beanie, to the one before. So I'm going to bond 1 to 0, 2 to 1, 3 to 2, all the way up. Cool? That's it. This is just some commands so we can live visualize. And then I'm just going to integrate this up to Tmax. And I'm going to integrate 100 times because my time set is 0.01. So 100 times 0.01 means every 1 simulation unit. Cool. And then this command just visualizes. Okay, let's see what this is. Okay, there we go. And you can't see it. There we go. Yay. Okay, look how much faster this is. Oh, wonderful. Looks like a friend. Cool?
Yeah.
All right, cool beans. Everybody cool with what's going on? We're going to use simulation packages so we can keep going and still have simulations happen fast. Okay? We'll still do our own coding if we don't need particle interactions. All right? Okay. So there we go. Now, we can do fun things. Of course, I'm biased. Let me load this one. So let us change our cutoff. Remember, it's 2 to the 1/6 times sigma. Let's make it 2 times 2 to the 1/6. What do you guys think is going to happen?
Can we get attractive or something?
Do you think Martin's right?
RC is the cutoff.
Yep, RC is a cutoff. So
We've done
remember,
it.
our potential looks like this. We cut it off here, and now we're extending it. What does it look like beyond this?
So we're just moving it that way? It goes back?
Nope. Yeah, exactly. I'm just moving it in this direction. Yeah. Goes back up, right? Like this. Because we have that shift, it's going to approach 1 here, but again, we're interested in 4, so we don't care. So Martin is right. We should get attractive forces. Okay?
But doesn't that also mean we have kind of something further too? Although
What do you
I guess that's kind of hidden in between. Like if we shift our cutoff, we still have this discontinuous contraction.
Yes, we do. You're absolutely right. Okay? We're not going to worry about that.
Yeah, but that was kind of, I like the ends kind of come up first.
Yes.
Oh, cool.
Okay. Okay. So we can get this type of behavior. All right. The monomers are attracted to each other. It is weird, isn't it?
They need
Just turn
Singularity.
into, turn into a gigantic ball.
The end of the universe.
that's very anticlimactic.
Sorry. We can change epsilon. Okay? We don't want it to be so dramatic. Let's change it to only be half a kT. So now, I know. No. So now, is this just a fun thing to do, or do you guys think this has any relevance? Oh. That's a very good answer. What could be a relevance thing where this might be relevant? This specifically? Or in non-specifically? What do you got? Scaling will change, right? We talked before about how scaling is a random walk, and then if we have excluded volume, it changes from that, and you have stuff like this.
I mean, if we're looking at like polymers like coiling inside like a cell or something.
Where might this actually happen? Where might you actually see something?
Something?
Sure.
A polymer that can stick to it.
Sure.
So high protein and water. So that makes sense.
Yes. Okay. So this and what you just talked about can be characterized as the solvent polymer. Okay. Polymer terms. So if you have a polymer in a poor solvent, polymer doesn't want to dissolve in that solvent. It would prefer to interact with itself in the solvent. You can get these kind of effects. Okay. And then you can have a good solvent where it is just as happy to interact with the solvent in itself. And that's basically what we need. There is, now the scaling will change, right? Because in a very poor solvent, how do you expect the scaling to scale?
You can scale out more of what?
The scaling of the radius of gyration with the polymer size. So remember we said it's a random walk, so it was 1/2. And then we said, no, we have excluded volume, so it's bigger than that. It goes as approximately 3/5 or exponent 3e. If you're in a poor solvent, what do you expect? What should RG scale? Okay. To give you a hint, let's make this a very poor solvent. Epsilon 5. Doesn't crash.
Yeah, they should just
So poor solvent means more.
Polymer wants to stick to itself, doesn't like the solvent.
Okay.
What kind of object do you expect at the end here? We let this go long enough, so it finds a global minimum. What should it look like?
sphere.
A sphere. So how should the scaling of RG go with that?
Just so many. Or
It's just packing in 3D. So
should just scale with essentially the volume of
and how does the volume scale? Yeah. Right? 1/3. Are you guys okay with that? So we go from 1/3 if we just keep packing everything together in space, right? When it's an ideal random walk, we go to 1/2. Then we have excluded volume, we go to 3/5. Okay? So as we go from poor solvent to good solvent, we go from 1/3 to 3/5. Cool? Now somewhere along the line, what will our scaling exponent be?
you said it's a
1/3 to 3/5, and there's a special value. Random walk. Right. 1/2. Right? 1/2 is a very special number, right? Because that defines diffusion in random walks, right?
Yeah.
So there's a special type of solvent called a theta solvent. Okay? Where you basically get ideal scaling, even though, of course, in reality you have excluded volume. Cool. So it's just fat enough to overcome exclusion. Cool. Neat. Dropping a little polymer physics. You're not taking time to do it.
That's an awesome shape.
I'm glad you're impressed with this one, Martin. Cool. Is everybody okay with this?
Yeah.
Yeah? So we can use simulations to simulate different solvent qualities, okay? Just by playing with these parameters, our epsilon and our cutoffs. Cool. That's really okay. Okay. Let's go beyond two-body interactions. What comes after two-body interactions?
M-body interaction?
No, you really like to jump to the end, right?
3. Just
3D.
Just bump up to 3.
Why might I want a three-body interaction? Remember, this was our two-body interaction, basically a spring. Why might I want a three-body interaction?
Okay, the effects of, so you have like, your ball spring ball. Obviously, the effects of one are going to kind of rotate the other one as well.
Nope, everything is additive.
Everything's additive.
Yeah. So, you don't have to worry about that. Pairwise additive.
But you say we're not worrying about rotations? My initial thought was that we could change the angle now.
What kind of mean rotation?
Like,
You're right.
change the orientation.
So 3 bodies, where should I draw one body? One body draw.
Sure.
Yeah.
I just meant like, if you had it.
Yeah. Awesome.
And then switch orientation.
Exactly. Yeah. Okay. So we can define a bond angle, theta. Okay. So for example, water. I mean, who cares about water? But let's just say we care about water. We can define a bond angle, right? Now, this bond angle is kept in place. How is this bond angle kept in place? Why does water look like this instead of being in a straight line? Yeah, we have to do paired electrons, right? Look at their shells. They're sitting out. Okay? And so we have this angle here, which is angle equal to.
What is it like 100? No, sorry. This is
I was thinking
102?
108 or 108?
This is awesome.
Yeah. I forget. I like this is like a thing in Chem 1. This is on like
Approximated by
It'd be all.
Was it like 108, 112?
I have a somewhere between 90 and 180.
112.5?
So this is, and there's actually 2 different numbers, right? There's the ideal tetrahedral angle, and then there's, because of the effects of the cloud being more smeared out, there's the actual angle.
And then there's the experimental.
Yeah, so like 104.9.
104.5 is the experimental.
Okay,
And then 109.5
Yeah.
is based on the test for model.
okay.
So the answer.
I don't know, I think one of you got it right somewhere. There's a whole lot of numbers.
Every number between 100 and 130.
So 108 and 112.5.
Okay, so let's say we want to do simulations of water, and we're happy to have an oxygen and 2 hydrogens. Okay, we don't want to include these electrons. That's crazy. Okay, what can we do? Well, let's impose a potential where we have theta naught to be equal to 104.5. Okay. So how can I do this? Well, it's the easiest is to just have a harmonic bond. Cool. So the further your angle gets larger than this, there's going to be restoring force to go back. Smaller it gets, restoring force to go back. Okay. This is not always the best potential to use, even though it's very conceptually simple. Okay. This is not continuous if you had a bond that could actually flip around like this. Okay. So there's ones that instead you have cosine of the angle in here instead of the angles. Okay. Again, not so worried about the details. I just want to motivate. This is why you need a 3-body interaction bonding. Okay, people in my lab, what's a very important case where we need a three-body interaction?
Whenever you're looking at the rigidity of the polymer,
Yes.
then you need
Okay.
to include
If we have a freely jointed polymer, like we're looking at so far, then we can just have, we don't need any bond angle. But let's say we have a polymer that has some stiffness to it. Okay? Well, now, this guy, the direction of this guy is correlated to this guy is correlated to this guy. You can actually look at those correlations and calculate what's known as the persistence length of the polymer, which is really just a measure of the stiffness. Okay? How can we do that? Well, we can just impose a bending potential here, okay? So in this case, theta naught would be equal to 180 degrees, and the persistence length is approximately equal to the stiffness K in the harmonic potential. Okay? This is only true, this is not so true when you're looking at very short lengths because of the finite.
That's for a bond length of 1, right?
Yes, correct. Cool. So if we want a stiff polymer, we can just use a three-body interaction. Let's do that. Okay, so my code is going to look exactly like it did before, or almost exactly like it did before. And the one thing I'm going to add is this command here, which is I'm going to define a new type of interaction. I'm going to give it the label 7, for whatever reason. And it's going to be an angle, and it's going to have a spring constant of 10, and the default angle is 180 degrees. Now be careful, most programs use radians as input. Okay, I have had to regenerate simulations because I put in 180 and it was in radians. I have very funny behavior. Okay, that's why I don't even include it. All right.
Is 10 part of that set of coefficients that was shown to be very thick?
No, no. 10 is, this would give an effective persistence length of about 10.
Right.
Bond lengths.
But I mean numerically.
No, because, watch. Why talk when you can watch?
Really?
Yeah. Hey, here's our famous polymer. Okay. Okay, so that's without, I think. Oh.
Yeah, you have one of the if statements.
Yeah, so I also have to include that potential when I define the polymer. Okay? Now this is a three-body potential. So now I have to do it if I is greater than 1. What I'm going to do then, so let's say I start at 2. So this would be, I'm going to have 1 as my central monomer, and I'm going to have 2 on one side and 0 on the other side. Okay, so that defines the angle. This is 1, this is 0, this is 2. That defines the angle 0 to 1, 1 to 2. Cool? All right. So let's see what happens if I include that. No. I didn't say that. Phew. Okay. Now we can see it's not freely jointed. Okay, there's a stiffness. Cool. Now in terms of why is K 10, well, what happens when I make K 100? Just changes the stiffness. So K is whatever we need it to be to get the stiffness up.
So, but if we started from, we initialize the monomers in not a straight line, or if the angle of the potential was not 180, if we made it too stiff, it would explode.
That is your problem. Okay, initialization, stable initialization always depends on your model and what you're submitting. Okay, I mean that's like saying, whoa, 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 whoa. When we do non-interacting particles, they can sit over top of each other. Now we have excluded volume; they can't sit on top of each other. Yeah, no, of course, yeah, that's your problem.
Yeah, fair enough.
Cool. All right, any questions on this? All right. No questions, then let's keep going. How about a four-bodied interaction? When might we possibly want a four-bodied interaction? Done 2, done 3, 4 is next on our list. Or do we not want to bother?
When you have chains, thinking of like,
Pardon me?
I think I'm like when you have chains where it's like
So why can't we just do that with Monday?
I guess you could do that. Okay, maybe that's not regulated.
No, it is. But you got to think more than bond angles are really just a 2D problem, right?
So this brings it in.
We just did 3 portion. It'd be way nicer if all molecules. Okay. So what that means then is we could have 1, 2, 3, 4. That's something like this, right? And these angles, this angle and this angle, can totally stay the same, but it can rotate like this. Right? I'm not violating any of my angle constraints, but I'm totally changing the configuration. Okay? Cool? Everybody okay with that? This is why we need a four-body interaction as well, because of the 3 dimensions. Cool? How can we control this? Well, we can define 1, 2, 3 to be a plane, and we can define 2, 3, 4 to be a plane, and then we can just have a constraint between that plane and this plane. Cool? We can measure an angle between those 2 planes, and then we can have a restoring force based on that.
So are these getting expensive computationally? These
Yeah, but it's not so bad because the bonded, you always know your neighbors, right? So bonded is not too bad. So first of all, non-bonded is bad. Long-range non-bonded is death. Not death. Cool. Is that okay with people? Anybody know what these are called? Oh, I don't know which one's the good one. Anybody know what these are called?
If I remember correctly, these dihedral.
Dihedral. Okay.
Let's just think back for a second.
You're probably
Yeah, that's actually true. Okay, so there's actually 2 types of dihedrals. So the one I just showed is called proper dihedrals. And there's also improper dihedrals. Let me just show a quick picture. I'm not going to draw this. There we go. Okay. So the one I just talked about was this guy, this proper dihedral. Okay. But there's also this guy. So let's say we have this scenario. Okay. So the base of each marker is an atom, and then there's the 4th one that's sitting in a plane above it. Okay. We want to make sure that it stays above it, that it doesn't flip around to be this. Okay, that's called an improper dihedral. Okay, it's very important for things like chirality. Okay, cool.
So it's a normal called a proper dihedral?
Yes. that cool with people? Yes, no, maybe? Okay. And we can stop at four-body interactions. We can do whatever else we need for four-body interactions. Cool? When we eventually exist in four spatial dimensions. That's how I understand it. Then we might need more. Okay, so here I'm defining a dihedral interaction. Then you have to define a bunch of parameters, which will leave it up. It's not too important. But I want to make a certain class of objects. Okay. And the objects I want to make, because I want to use them later in the course, are basically cross-like particles. Okay? And so I want them to be essentially two-dimensional with a center object and then objects on either side in X and Y. Okay? How should I do this? You can also think of this as a really primitive set model. What should I do? So I can make four objects and I can place them here. Okay? That's a position, but now I need to do the topology. How am I going to connect them together? Any suggestions?
Well, to start, we can use Feeney bonds between the top to the center, the left to the center, the bottom to the center, and the right to the center.
So Austin really shouldn't be answering this.
Sorry,
This is what he does for a living.
sorry. I won't say anything.
Ah, you got us off. Okay, so I can use two-body interactions to make that. Okay, if I don't put those in, this thing's going to fly. Right? That's cool. So let's see what happens if we do just those. Okay, and so what I'm going to do, I got to show code.
Yeah, so excited. I can answer this.
Okay, so I can have a loop over however many cells I want to create. And then what I'm going to do is I'm going to set a central cell, which I'm going to call PC. And then we're going to have P1, 2, 3, 4, which are the ones on the outside. Okay? And so I'm going to place this one at some X naught, Y naught, Z naught. Then P1 is going to be 1 to the left. This is going to be 1 to the right. This is going to be 1 down. This is going to be 1 up. Cool? And what I'm going to do is I'm going to link the central to each one of those. Let's see what this means. There's all my little crosses. But when I zoom in, they are definitely not keeping the topology. Okay? Those are not all nice little 2D cross shapes. Okay? What should I do? This isn't good enough.
Well, that would use our three-body potential.
What these are three-body
Top, middle, bottom.
top, middle, bottom?
I would do that.
So we could have that be a stiffness?
Yeah.
Yeah. Can do that.
Or we do the two-body potential between top and bottom. Or we could do the four-body potential between tops. Or we can use the improper type between the top, left, bottom, and middle. And then another one between the top, right, bottom, and middle.
So first of all, let's try and keep our ring as a ring. Cool. Let's keep all these guys in the same. How can we do that? Can do a proper dihedral like this, right? 1, 2, 3, 4. Actually, it doesn't. 1, 2, 3, 4. Cool. Everybody on board with that?
Am I going to break symmetry?
That'll be fine. All that's going to do is keep it in a plane. That's it. Okay? Because I can set that angle to be 0. Right?
Yeah, but when it bounces about the plane, it can do it on one side and on the other.
No. So it's like this is a plane and this is a plane. So I guess so, but we can just tighten it up.
We should just do 2 planes and then crank the step.
Yeah.
Cool. So there are many ways to do what we're trying to do. We're just trying to show one way.
So doing something like setting K to like 10 billion or whatever.
You can't have it too high, it'll crash.
Okay, no.
Yeah. For the same reasons. Yeah. On purpose. Yeah. We'll find your dream. So if I do that, let's see what it looks like. It's getting there. Okay, so try and stop this. Those guys are more existing in a plane now. The issue actually is the center monomer, where they can pop from side to side to side. Okay, so what can we do there? Well, we can use a improper dihedral. Keep it in. Cool.
Can you show the code where you define bonds?
So this is basically K, and this is basically the angle. The equilibrium angle.
So proper and improper dihedral are defined the same.
In Espresso they are. Some packages they're different. Okay. So I have to be careful how I define this improper dihedral. The central particle actually needs to be last. It's just an extra parameter in the definition of that. Cool? Is this okay with people?
So we're just using the proper dihedral to pull it the other way.
No, to keep the central one in plane.
So our 4 circles or our 4 particles on the outside are locked in one plane, but the one in the middle can still pop around freely. There's
Yeah,
nothing
the-
to prevent it.
Proper dihedral. I thought that one was where it's like like that. But
Yes, we're doing that where 3 of the satellite ones are the random.
so we're just using
Yeah. All we're doing is keeping it in plane. Okay, we're not talking about any other restriction limits. Cool?
so the angle up will just be like
0.
0.
Yeah.
Okay.
Cool, it works. It's keeping these guys in plane. Cool. So just 2 impropers, just 2 dihedrals can keep all these particles in the same. Achieved our 2D structure. Cool. It still doesn't look perfect. What else is going on? This doesn't look like a cross to me.
Can wobble.
Yeah. How can we fix that?
3 body bond.
Yes. Okay. So let's just put a 3 body. This has got to be 90 degrees. This has got to be 90 degrees. This has got to be 90 degrees. That's got to be. Cool. That's what these guys are here. These other guys here are the stiffness that we talked about that we could also do over here. Okay, I don't think we need it, but
Well, there's a couple things that might change, but yeah, pretty much.
okay, pretty good to me. Okay, they're nice and 2D, and they're mostly keeping the cross. And if we want it to be really rigorous cross shape, then we can crank up the K even more.
Well, I think we did good.
I added bond angle like this to be 90, bond angle like this to be 90, bond angle like this to be 90, bond angle like this. Okay, so that is this interaction that I call 8. What does 8 look like? It's just a bond angle where the equilibrium angle is 95. Cool. Is this okay with you? Okay. Now you can do fun stuff. Okay. Yeah, you can make complicated things.
Yeah, you go ahead.
Okay, because what can we do? Well, let's say we have these as objects and we want to look at how they are going to coagulate together in solution. What we can do is we can start introduce an attraction. So we would increase our cutoff distance. Okay, this is a weak attraction.
Epsilon to 5.
Yeah, let's crank up epsilon. Redoes it. Okay, so now they're starting to stick together. Get these extended over.
That's cool.
Cool. This looks a lot like some research. Cool. Okay. I have a topic in here. Motion of aggregate particles. I want to do that. Yeah, let's do this. Well, actually, while I have this screen, we'll get to that later. But let me show you, while we're on this topic, what we can do with the extensions we've learned. So let's look at self-assembly. Okay, and so we're going to define some objects. And let's just run it. Okay, so here I'm going to have objects that have blue head and a red tail, and the blue heads are attracted to each other. Okay, not the red tail head. Okay, and so I'm using bonds to link these together. I'm using different types so that the red have just excluded volume interactions, but the blue have an attractive tail. I'm also using a stiffness, so these things are nice and round. Cool. And so we can show how shapes like these would actually be formed if we had a bunch of these in system. Cool. So it's easy to imagine how you can extend this to how you could study like micelle formation and lipid bilayer formation and all that kind of stuff. Hydrophobic interactions driving proteins. Protein. Cool. So assembly is a huge field. All right. Let's look at another cool one. Okay, these are double-sided. Okay. And again, the blue is attracted to blue. Okay, but now, because they're double-sided, we're actually making these cool things. So you can get all sorts of interesting phenomenon once you start connecting particles together and defining different informations. Okay? And again, this is a very big and very active. Okay? This is an example of like something like a block copolymer. Polymer made out of two different molecules.
The one on the left-hand side has like a little triangle that has a bridge. Stable. That's really cool.
Neat. Oh, hey.
Yeah, that's definitely really
Okay. And then you can also do things like this one's called Big Head. Okay, because what I did, you won't see it right away. The head on those blue guys is going to be massive. Oh, wrong one.
Yeah.
Something like that. Oh, wow. Okay. And so I think here the tails are attracted to each other, but not the heads. Okay. And so here again, I can just use different WCA interactions between blue-blue, where there's a very big sigma, sigma of 5. Between red-red, it is a sigma of 1, and there's an attractive tail. And then between blue and red, I can just use my combination. Cool? Neat? Fun, eh? So self-assembly is a good project topic, except for Sarah. You get it in the summer. All right. Polymer physics is another very good topic. It's like something how you simulate. You must be careful how you simulate. Okay. I have a neat story that I'm not going to tell now. About how you can get exactly opposite results depending on how you simulate also. Okay. Cool, is that cool with everybody? Okay, so building things out of particles, you can use simple potentials to construct complicated objects. Okay, and we'll need that for later stuff like when we get to granular material. We're not going to want smooth balls anymore. We're going to want friction to naturally emerge in our system. So we're actually going to make it out of discrete particles so that we get rooms and regions. Cool. Okay, a couple minutes left. Let's talk about motion of aggregate particles. Okay. So let's say we have some aggregate particle. Okay. Now, how would you expect the diffusion coefficient to scale with the number of monomers? Any guesses? So if you take one monomer, has a diffusion coefficient of 1, join it with another particle, the diffusion coefficient goes up, stays the same, goes down. Why down?
Bigger particle, but more track. Thermal kicks aren't necessarily coherent.
Exactly. Okay. This guy has a thermal kick. This guy has a thermal kick. If they're the same direction, that's great. Okay. But if they aren't, then they compete. Okay? And as you add more and more and more, eventually you're going to have 0 effective thermal kick because it's just going to average. Okay. So D, in the absence of any hydrodynamics, scales as 1 over. Okay. Now, if we put a force on this object, okay, every monomer feels a force F, then the net force is just n times this F. Yeah? And what this means is that the drift velocity, which is, we solved for this, F over zeta. Okay? And the reason for this is that the increase in the total force scales as F. As Martin pointed out, increase in the friction scales as F and exactly cancel. Okay? So if you take an object and you attach a bunch of other particles, similar particles to it, the drift velocity you get at the end is the same as if you have. Okay? This is okay with people. Yes, no, maybe? Now, if you have a rigid object and you start to look at hydrodynamics, so we start to look at the effects of the solvent, it very much depends on the shape of the object and how it is oriented, right? So a rod going through a solution like this or like this will have different friction coefficients, okay? Surprisingly, only applied something like that. Okay. Now, let's think about having a flexible object like a polymer. Okay? Yeah? They're already with me right now. All right? And we want to look at the diffusion coefficient. So by this argument, D should scale as 1 over n. Anyone think of why that might not be true if we include interactions with this? Because remember, this result is true for Longevin dynamics because we have no solvent. The solvent is implicit in our equation of motion, right? We can't get any interactions through the solvent because it's not actually there.
Well, the solvent can become correlated.
Yeah. Okay. So let's say this guy is moving in this direction. Okay. And it pushes all the water between this guy and this guy to push this guy. Okay, so there can be correlations through the solvent. So this means that D actually scales as 1 over n to the 3/5, which you should recognize as a force. Cool. So notice that means D does not scale, does not decrease as quickly as you increase n as it does in the absence of hydrodynamic interactions. Cool? Is that okay with people? Yeah? Okay. A question for you. Why is it then that DNA is so-called free draining? Okay, this is free draining. Free draining means regardless of how big you are, you have the same grip. And when you actually put DNA of different length strands into a solution, you apply an electric field, they all go the same speed. Why is that?
Yeah, I would think that because the DNA is charged itself, that if you apply an electric field to it, the longer you are, the more you're going to interact with the electric field.
Yeah, well, that's exactly what we said here.
Yeah.
Right? So the external force scales as NF. Right? And if D scales as 1 over n, we get free draining. But if D scales as 1 over n to the 3/5, we don't get free draining. Right? Because n over n to the 3/5 doesn't equal 1.
Right. Wait, that's diffusion.
This is diffusion. This is force. This is also diffusion. This is diffusion without hydrodynamic interactions. This is diffusion with hydrodynamic. Right? So without hydrodynamic interactions, they exactly cancel.
Well, DNA shouldn't have this because it should go into this.
Which means the ends shouldn't cancel, and you should be able to do free solution electrophoresis. But you can't.
Yeah.
It's a very physical reason. People know what I'm talking about? Yeah? Everyone understands the question? Right. Basically, why does D scale as 1 over n, not 1 over n? For DNA electrophoresis.
That is the answer. That D does scale over.
Well,
Because the alternative is that F scales.
no, F is cool. Yeah, F is good. Okay. We have to be careful about D because I'm not talking about equilibrium property. Right? So like D is a transport property, but I'm talking about it in the presence of it. Okay? So we have to be careful, but effectively yes, because really this is the same as saying how does the friction scale?
Yeah, but so one of the things I was going to say is that maybe the charges on the DNA create shells so that the total force is less than and that.
Don't worry about that.
Right.
That can be true, but that will happen to the same degree for every monomer. And it will still scale as n. They're just going to be a prefix.
Would the, no, I guess I was gonna say the persistence length of DNA is long enough that the interactions are kind of far away each other.
don't worry about
That doesn't.
So is it just that it has to carry all that water with it?
No.
Is it that it forms a phosphate diagram?
What it is that DNA is negative. We're driving it in this direction. We're driving a bunch of positive ions in this direction. Right? The positive ions rip through your DNA polymer and destroy any hydrodynamic. The whole reason for this refit goes away because there's some other stuff going between the polymer itself that destroys it. That's how we get back to refit.
If you had a solvent with no positive ion, that would be the same problem.
If it didn't disturb that flow, then I think that should be okay. It's something to try. You could do it in simulations by including solvent. See what you get. Cool. I know we're out of time, but let me just show you. Okay, so this is why people do gel electrophoresis. Okay? Because if you put in a bunch of obstacles, like we see here,
The board's not there.
That's okay. We can see.
oh, bond broken.
Oh no! I think you just randomly put a particle where your coastal is maybe.
Yeah, my this code work, damn it. Once upon a time. Okay, we'll have to look at this at the beginning of next class. Okay? But we can, based on what we learned in class today, we can easily simulate polymer gel electrophoresis. So driving polymer obstacles, and then you recover length.
Yeah. Like cyclic monomer for polymers, it'd be easier just like I would think this is really like cyclic polymers.
Yeah.
So like benzene. Would it be easier just to create an attractive end so that you can have end simulation, or just construct it as a
You gotta be careful. If you want a covalent bond there, stick them on.
Okay.
Yeah.
Yeah. Oh, okay.
And if you do that, it's probably like crash.
Oh, okay. So you're like going to make a bunch of like cyclic polymers, just like create those.
All right, Kyle?
Yeah.
All right.
Yeah.
Look a bit confused.